May I have your attention? We resume the technical program. The next speaker is Professor David Stevenson with Caltech. We are now moving on a closer examination of the Jovian and Saturn. Okay. Please welcome Professor Stevenson.
Where's the laser pointer? It's gone.
The laser pointer was right. That's okay. I've got another one. Oh, there it is.
Oh, there it is. Well, it's a delight to be here and participate in this symposium that honors a giant in science, Galileo. And, of course, for many people, the fame of Galileo is tied to these observations. And indeed, the Galilean satellites were the first planetary system other than our own to be discovered. And that's, I think, of great significance, aside from affirming the Copernican view. Galileo, of course, did look at Jupiter and Saturn as planets. His technology did not enable him to say a great deal about those planets, though he did notice that Saturn was kind of strange. It had handles, if you will, and this was eventually identified as the rings. My talk will focus on the planets themselves, and in preparing this, I asked myself, what else did Galileo do as a scientist that contributed to our thinking about planets and their interiors? And one of those things is this device, which he invented, the Galileo Thermometer. This is a model of it, not the original. And it's based, of course, on the concept of buoyancy. And this, of course, is a fundamental idea for how we think about the distribution of materials in a planet. So you could think of this as a model of a planet. But of greatest importance is something that has already been discussed at this symposium, and that is that Galileo was truly a pioneer in the modern scientific philosophy, how we think about things. And we've already seen this quotation, "The universe cannot be read until we have learnt the language and become familiar with the characters in which it is written." And this is a central idea to how we do science, and it came from Galileo in large part. So if I'm going to tell you something about the insides of Jupiter and Saturn, I should first convince you that this is of interest. Jupiter and Saturn are the most massive planets, but there's more to it than that. In forming those planets, we defined the architecture of our solar system. In our current understanding of planet formation, it is that massive body, Jupiter, that in large part dictates the rest of the evolution. The current models for the formation of the Earth depend on where Jupiter is, on whether it is in a circular orbit or not. The slight eccentricity of the orbit actually matters. And they depend on the timing, how long it took, and the process whereby the planet was built. So in a very real sense, the nature of our solar system is intimately tied to our understanding of the formation of Jupiter and, in turn, the structure of Jupiter, because we believe that Jupiter retains a memory of how it was put together. That alone is sufficient motivation for wanting to have a really good understanding of what goes on in those planets. In addition, if you are a fundamental physicist, you care about what goes on in planets such as Jupiter, because the material inside is a very interesting state of matter, It is a Coulomb plasma in which the electrons are degenerate. It is a liquid metal of a particular kind. It is metallic hydrogen. As if that were not enough, we have, of course, all the fascinating phenomenology that we can see and try to interpret. The strong winds, east-west winds, great red spot, the magnetic field, the clouds and how they move around, and, of course, the satellite system, which is part of the formation process, but which I will not talk further about. Now, Jupiter, as the most massive planet, is also a planet that is made of the most common material in the universe. Most common baryonic material that we know about, which is hydrogen, left over from the formation of the universe, and helium, which was also created at the time of the Big Bang. In a very real sense, the recipes for planets are determined by nuclear physics. Nuclear physics at the time of the formation of the universe, and nuclear physics subsequently through thermonuclear processes within stars. And what you see here is a list, a menu, if you will, of the materials from which you build planets. And in the case of a planet as massive as Jupiter, it will be unavoidable that the main constituent is hydrogen, with a modest amount of helium and small amounts of the rest of the stuff because they are small in abundance. Still of importance, and of course for us here on Earth, made out of the dirt, the small amounts of magnesium, silicon, and iron, and the oxygen that goes with them, these materials are of interest to us, but the giant planets in our solar system and elsewhere are unquestionably made of hydrogen, and when you try to make a model, a theoretical model, of a planet such as Jupiter, you find that hydrogen is the only material that works as the dominant material. Hydrogen is very special because it has 1 electron per nucleon, 1 electron and 1 proton. All the other materials have a different mix of electrons relative to nucleons, and that makes a fundamental difference at high pressure. So what then of Jupiter? Go with me, if you will, in a ride, a hypothetical ride from the atmosphere down into the interior. If you're out at this outermost thin shell, the part that you can see through a telescope, you're in a region where the density is even lower than in this room, the air in this room. Gas, mostly hydrogen, but small amounts of other things responsible for the clouds. As you go down, the material becomes hotter and more dense, hotter because there is energy coming out of the interior of Jupiter, energy of formation. Unavoidably, when Jupiter formed, it was hot, tens of thousands of degrees. That heat is still leaking out. And already, when you go a small distance below the surface, the density has increased dramatically by orders of magnitude. And the way to think about this is that you start with a material where you have molecules of hydrogen that are well apart from each other and therefore don't care much about each other's existence, and so it's just like billiard balls bouncing into each other in ideal gas. And then as you go up in density, those molecules get closer together, and at some point when the molecules get close enough to each other, it's not clear to an individual electron whether it makes sense energetically to belong to this pairing, which we call the hydrogen molecule, or to become part of a Fermi sea of degenerate electrons. And indeed, that state begins to become apparent from experiment and from theory already out in this region, 85% of the radius, where the material is beginning to become metallic. Now, we call Jupiter a gas giant. That doesn't mean that you should think of it as if it were a gas. It just means that the stuff from which it was made was gas at the time it was assembled. But of course, when you subject it to the high pressures due to self-gravity, then it becomes a liquid metal. It's the same stuff, but the words, gas giant, are a little bit misleading for that reason. So the idea is that most of the stuff colored here in orange is, in fact, a liquid metal, albeit at quite high temperature, 10,000 degrees or more. Jupiter is not just hydrogen and helium. We find that when you try to make a model of a planet like this, you have to put in other stuff. We also know from observation, both spectroscopically and also the observations that Torrance Johnson mentioned with the Galileo probe, that there is an enrichment of the heavy elements. What that means is that the previous table I showed you for abundances doesn't fully reflect the composition of Jupiter. It does not have the composition of our Sun. It has an enrichment of the heavy elements. We see that in the atmosphere, and we also think that part of that may lie at the center of the planet as a core, a central region that is Earth-like in the sense of being dominated by those heavy elements, magnesium, silicon, iron, oxygen, perhaps water. And we don't know how much mass is in the core. It is perhaps 10 Earth masses. This is something that we would like to understand, and at the end of my talk, I will explain how we're going to go about doing it. It is of importance for understanding how Jupiter formed. You might wonder, how is it that we can have so much information already about Jupiter and not know this elementary fact? But keep in mind that 10 Earth masses is tiny. Okay? Jupiter is 315 Earth masses, so 10 is just a little bit. And so that's why it's hard to pin down. How do we go about understanding these things? Well, a major part of it is quantum mechanics, along, of course, with experiments. And here are some examples of solutions to Schrodinger's equation using density functional theory. On the left, molecular hydrogen with some helium, and on the right, metallic hydrogen, also with some helium. Several groups are involved in these calculations. This particular simulation happens to be the work of Burkhard Militzer and his colleagues at UC Berkeley. This is a major computational undertaking. It could not have been done 10 years ago. It is being done now, and so this is a very fertile field of science where there are dramatic improvements in our understanding. Another way of learning about these materials, of course, is to do experiments. And there are a variety of ways of doing this: shockwave experiments, experiments in diamond anvil cells. This is one particular way of doing it that came into operation just in the last year. It's the National Ignition Facility at Livermore. This thing cost $4 billion. It's even more expensive than a typical space mission. And you're only seeing half of it here. 192 very large lasers in a building that is twice the size of a typical athletic stadium, all for the purpose of focusing down onto a tiny deuterium-tritium pellet. The reasons for doing this are laser fusion and as part of defense interests, but a small part of this activity is directed towards basic science. Usually they're at temperatures higher than are of interest to Jupiter, but they can do experiments at the lower temperatures and pressures that will inform us about the behavior of materials inside these planets. Now, one of the things that we think is happening in Jupiter and in Saturn is that when you get down into this region where the hydrogen begins to be metallic, the helium doesn't want to mix with the hydrogen. The helium likes to stay in a neutral environment, and so it becomes insoluble and forms raindrops. So this dashed line represents a level. It may be 1 million atmospheres, 15% of the radius of the planet, down from the interior. This is an old idea, but calculations just in the last year, 3 independent groups, now confirm that this is probably happening. These droplets grow to a order of centimeter in size, and they settle just like in the Galileo thermometer. And that brings me to the noble gases as a general issue. Torrance Johnson showed you a slide of the observations for this, for indeed we see that in the atmosphere of Jupiter, helium is 10% depleted. This comes from the Galileo probe data. A small enough effect that some people wonder whether it was real, but for neon we see a large depletion. And it would seem that this is explained by partitioning into helium raindrops. The calculations submitted for publication by the Berkeley group show that this is indeed a good explanation. The heavy noble gases are enriched because they come in as atoms that are stuck on water ice. Heavy noble gases stick onto water ice, and that material is therefore information about how the planet was put together. There is also in the new quantum mechanical calculations evidence that argon, at least, will partition upwards. In other words, it will go in the opposite direction from neon. And interestingly, neon is a Jupiter thermometer. The observed depletion, this factor of 10, requires a temperature of about 5,000 Kelvin at the place where the helium raindrops are forming. This story is now falling into place with all of the details coming from these very complicated computer calculations, solutions of Schrodinger's equation of a kind that were previously not possible. Now, I mentioned already the issue of the core. Why do we care about whether there is this core made of heavy elements? And the answer is that it informs us about how the planet formed and evolved. In the case of giant planets, what we think happened is that it's a bottom-up process. Bottom-up means you first assemble a core made of the heavy elements, you then put the gas on top. The assembly of the core itself is informing us about what happened in the very earliest solar system, and by knowing the mass of this, we can place constraints on the environment in which the planets in general formed. Just for comparison, I should point out that in the case of us, Earth, it is not bottom-up, it is top-down. Top-down means that we think that as the Earth formed, it was a mixture of the stuff that goes into the core, which is liquid iron, and the silicates, which are the rocks immediately beneath us. They then separated under the action of gravity, and so that's a differentiation process quite different from the giant planets. Of course, in the case of helium specifically, to the extent that it differentiates downwards, that is a little bit like the top-down process, but the main one is this top one. What about Saturn? Well, Saturn is, in fact, similar to Jupiter, except that the metallic region, the metallic hydrogen region, is deeper down. It does have a helium element enrichment. In the case of Saturn, the core, this heavy element part, is a bigger fraction of the total. So even though the data for Saturn are not quite as good, the confidence with which we can say that Saturn has a core is greater, and it is of order 10 Earth masses, maybe more. So Saturn is further away from the Sun than Jupiter is in terms of its bulk composition. I want now to say a few words about the magnetic fields of these planets. Here is a diagram showing Jupiter with the rotation axis, with its slight obliquity, and the magnetic field axis, which is tilted away. That is, the dipole of Jupiter has a tilt of order 10 degrees, actually very similar to Earth. Saturn, strikingly, has rotation and magnetic field axes aligned. In addition, the magnetic field of Saturn is somewhat smaller. What's going on here? Well, part of the story is just simply the fact that these planets, like Earth, can run a dynamo. By the way, one of the originators, very important pioneers in dynamo theory, is right here in the audience, or was a moment ago. That's Gene Parker, who's speaking later. The velocities and electrical conductivities are such that the conditions can be satisfied for a dynamo, and so both Jupiter and Saturn can do what Earth does because the hydrogen is metallic. And yet Jupiter and Saturn are different. I think what's going on there is related to the helium raindrop story, for indeed it turns out that if you form helium raindrops, you also form a layer of stability, meaning that you can't have convective motions through that region. That region will have winds because of the equator-to-pole temperature difference. Those winds will act on a field with dipole tilt to reduce the dipole tilt as seen from the exterior of the planet. This is basically the electromagnetic skin effect. If I'm moving with a conductor and I have a time variable field as a source beneath me, it will be attenuated. The time variability, or equivalently in this case the dipole tilt, will be attenuated externally. And just in the last year, there have been a couple of detailed calculations that support this idea. However, since Jupiter is also raining, it would seem that what one has to say is that this region is thicker for Saturn because Saturn is colder, the differentiation of helium is greater. If that is the explanation, then we should see a little bit of an effect of this attenuation for Jupiter, and that is something we can test. One of the other factors here is the winds in the atmosphere and the nature of the flow inside the planet. For one of the ideas with these planets is that the flow is on cylinders, as dictated by the rotational regime, and the idea is that the winds we see in the atmosphere may penetrate deep down. We do not know whether this picture is true, but all of these ideas will come together in the question of what we can learn from a mission that will be launched in 2011. It will arrive at Jupiter in 2016. It's called Juno, billion-dollar mission. And this, I believe, will answer many of the questions that we have. Here's a representation of the spacecraft, solar-powered. It will do microwave sounding, mainly to find water. That will set one of the constraints for internal structure. But importantly for my story, it will give us exquisitely accurate determination of the gravity and magnetic field, spectacularly accurate representation of those fields. This is a remarkable mission in terms of what we can learn from it. As you might guess, I'm involved in the mission. By the way, there's a large Italian involvement. Angelata, Luciano, yes, various other people in the Italian science community are involved in this mission. How are we going to figure out this high-density core, if there is one, and I think it likely is there? In the case of Jupiter, well, certainly getting the water is important. Knowing the equation of state is important, so we want to have that input from the theorists and from the experimental work. We want to measure the gravitational field very accurately. There are a variety of other things we can do. We can detect the tides, that is, we can detect the slight distortion of Jupiter due to Io. We can measure that to three-figure accuracy. That will give us something called the Love number. We can probably get the precession constant, which is the way you get the moment of inertia for the Earth, because indeed Jupiter does precess under the action of the Sun. That requires collecting data over the period of the mission of order a year. I want to finish off by just making a comment about the connection between our understanding of Jupiter and Saturn and planets in general. You will hear later in the symposium about extrasolar planets, but here is a figure published today in Nature. This is today's issue of Nature. And we now have, I didn't check this morning, but I think it's about 420 planets have been discovered. Most of them plotted here, variety of techniques. I'm not going to spend time on this, but I use it just to remind you that this is a spectacular development in science in which we are going to be able to make a connection between what we are learning in our solar system and what we are learning about other solar systems. And it's not just detection in the sense of knowing they're there through measuring radii, which you can do by the transit technique. For example, in the case of the Kepler mission now underway, we can learn about radii as a function of mass, and that tells us about composition. So I come to my final slide with the observation that we are doing what Galileo told us to do: measure what is measurable and make measurable what is not so. The things I've been telling you about, behavior of material at high pressure, the nature of Jupiter and Saturn, detection of extrasolar planets, these are in response to Galileo's request. Thank you.
There is time for one question. Please.
In your Juno mission, you mentioned determining the moment of inertia of Jupiter. From that, can you get the angular momentum of Jupiter?
The gravity field doesn't give you the moment of inertia and angular momentum precisely. Precession does, but getting the gravity field very precisely is important input into constraining the composition as a function of depth. Is that an answer to? I'm not sure.
I'm curious about the angular momentum value for Jupiter's rotation.
Are you asking about differential rotation, whether the inside and the outside are rotating at the same rate, that kind of question?
That is the problem.
Yes, that is part of what we will do. In fact, from Bill Hubbard's work, we know that a very precise determination of the gravity field in the higher harmonics will tell you about the winds, because the winds change, the differential rotation changes the shape of the planet. I've been doing some calculations myself to find out whether you can detect the Great Red Spot by gravity. It may be marginally possible.